Okay, I do have a couple comments on the homework. In 1 and in 3, there are questions about injection and surjection, or 1-to-1 and onto. On 3, I was a bit more particular than I was on 1, because 3, I just decided I'd be a bit more particular. I needed more than a yes or no. I needed some indication that you understood what 1-to-1 meant, what onto meant. So just yes on 1 or on 3. Yes was not enough. On 1, I gave a little benefit of the doubt, but by the time we get to 3, it's like, no, I really need to see an indication you know what 1-to-1 and onto means. So 1-to-1 again is no repeated outputs. And onto is we get all the outputs, or get all the possible outputs. And actually, I think on number 1, where people were coming up, the mapping was not onto, they typically did have an explanation of why. Here's an output we failed to get. So, with that, on both of these, we could go from a graph. So, say in number 3, the mapping was positive reals to positive reals, so that does not include 0, but we go from A to A squared, and we know what that graph looks like. The no repeated outputs is horizontal lines cross no more than once. All possible outputs is horizontal lines cross at least once. So if they all cross exactly once, then it's both. Now, that doesn't work in number 1, where the first question was, what about from integers to integers? Because we can't really think of the graph there. The 1-to-1 actually still does work. The onto does not, though, because we're only doing integers to integers. There are lots of holes in the graph, and so it's hard to see, does every horizontal line going through an integer actually cross the graph? Because we don't graph things with that many holes. Also on number 1, I gave you a function f, a function g, asked you some things about the composition, and then asked, is f an injection or a surjection? And what if we change the sets? Is f an injection or a surjection? There were some people that attempted to answer that question with f composed with g rather than f itself. So if you did that, it may have a comment, what about f or something not f composed with g? Okay, other questions on the homework?
I forgot to answer G, so can we on number 2?
Okay.
I forgot to answer that. Okay.
So 2G, we've got 1, 2, 5, 3, 5, 6, 6, 1, 3. And we want to write it as a product of disjoint cycles, because it's not disjoint now. 6 is in multiple ones, 3 is in multiple ones, 1 is in multiple ones, so is 5. They're not disjoint. So we can start with an element. Say we start with 1. 1 maps to 3. Is unchanged, 3 maps to 1. So ultimately 1 is unchanged. So we could write that down. but probably something's going to move. But 1 is unchanged, 2 is unchanged, goes to 5. 5 then, and remember with permutations, it's composition, we're going from right to left. I did have a few people go left to right. But this mapping is done first, nothing happens to 5, 5 goes to 6, nothing happens, so ultimately 5 goes to 6. Oop. Don't know that it ends yet. 6 goes to 1, which is unchanged, goes to 2, and so it does actually end at that point. But I didn't know it when I first put the parenthesis there. We haven't identified what about 3. 3 goes to 6, which goes to 5, which goes to 3. So 3 is unchanged. 4 never was changed by any of them. So we could do that, or we could just put 2, 5, 6. Normally we would only write the cycle of length 1 if we had to put something down. If it was the identity, we put one of them down just to show it's the identity. Other times we wouldn't put that down. Other questions? Yes.
So everything on here will be on the test. Is there anything not on here that'll be on the test? Like nothing with cyclics on here? Like.
What do you mean nothing with cyclics?
Well, like specifically asking like, is
I thought there were
this-
lots of questions about cyclic.
No, yeah, but like asking like in our notes, like,
Any questions related to secret that's not on this list?
oh, I guess, okay. I guess not specifically saying like, is this group a cyclic? I guess that's what I was meaning by.
Oh.
Which if it's a generator, then you know it is cyclic. But.
Yeah, I mean, 4, that was kind of the question, but I helped out a little bit by throwing out a candidate. You know, it's 7 the generator. 2E, we generated a cyclic subgroup. Theoretically, I suppose it could have been the whole group, although actually S8 is not cyclic. There's no... Okay, well, I won't pursue that. There are things we could look at in S8 to really sort of make a determination that S8 can't be cyclic. Pretty sure we could come up with that determination, but well, in fact, we could easily come up with that determination. This particular one, if it were in S8, would produce a subgroup with 3 elements. It's pretty easy to come up with other things that would produce subgroups of 3 elements. If it was cyclic, there'd only be one subgroup of 3 elements. And so that would be the most straightforward way to decide, well, S8 isn't cyclic. So I'm not going to ask you to take some huge group and decide if it's cyclic. It is possible for some smaller group, you might be asked, is it cyclic? And I won't make any suggestions on what you should try. But the process will be much like we did on number 4, just lacking the first thing you should try as a generator. Yes?
Can you look at E?
E? Okay. I assume, well, that would be 2E.
Yeah, sorry, 2.
So let's see, 2D, we got 1 goes to 7, goes to 8, goes back to 1. 2 goes to 4, which goes to 3, which goes back to 2, and then 5 and 6. And the reason I do that is we need that for E.
Yeah.
So this is our original permutation. And we want to generate the subgroup using that permutation. So the first thing we'll get is that permutation. 1, 7, 8, 2, 4, 3, 5, 6. The alpha. We'll need alpha squared. So we're going to combine this with alpha again. So if we look, say, where does 1 go? 1 goes to 7, goes on to 8. And notice none of the rest of them change 1. So ultimately 1 goes to 8. Where does 8 go? Nowhere to 1, nowhere to 7. Oh, I did it again. 7 goes to 8, back to 1. So it does close off that cycle.
Okay.
What about 2? Well, 2 goes to 4, which goes on to 3. And change 3 then, goes to 2, goes to 4. And 4 goes to 3, on back to 2. And what about 5 and 6? So 5 goes to 6, goes back to 5. 6 goes to 5, back to 6. So those two are not changed. We're not at the identity, so we've got to combine in another alpha. So alpha cubed would be this combined with this, alpha squared and alpha. We've not really talked about this, but the exponents work like we expect exponents to work. I mean, alpha cubed is alpha times alpha times alpha, that's alpha times alpha squared, or alpha squared times alpha. So to get alpha cubed, yes, we could do this 3 times, or we could just do the alpha squared, we've already done it twice, and then another alpha. So look, where does 1 go? 1 goes to 8, back to 1.
Yeah.
8 goes to 7, back to 8. 7 goes to 1, back to 7. So those don't move. Same thing with 2, 3, and 4, but we still have, or we get back now the 5, 6. The 5, 6 is only in the one place. 5 goes to 6, 6 goes to 5. So we're still not at the identity, so we're going to do it again. Let's see, alpha to the 4th. We could do alpha squared combined with alpha squared, or alpha composed with alpha cubed. Either way, we should get the same result. To me, this one's a little easier. 5 goes to 6, goes back. 6 goes to 5, goes back. But these are going to stay the same. And notice that is different than what we had here. Well, so if we'd have done this times itself, 1 goes to 8 on to 7. 7 goes to 1 on to 8. 8 goes to 7, back to 1. 2 goes to 3, on to 4. 4 goes to 2, on to 3. 3 goes to 4, on to 2. Alpha to the 5th. We could do alpha to the 4th and alpha, or alpha squared and alpha cubed. I mean, alpha squared, alpha cubed, probably is easiest. It's this combined with that. So 1, 8, 7, 2, 3, 4, 5, 6. And alpha to the 6th, there are lots of ways we could compute. We could do these two, we could do these two, we could do that one twice. That's probably the easiest, 5, 6 combined with 5, 6. That's going to be the identity. But if you really wanted to check, you could do this as well. 1 to 7, back to 1, 7 to 8, back to 7, 8 to 1, back to 8, 2 to 4, back to 2, 4 to 3, back to 4, 3 to 2, back to 3. Gives us the identity, or even these two. 1 goes to 8, back to 1, 8 goes to 7, back to 8, 7 goes to 1, back to 7, and that's going to happen with all of them. Once we hit the identity, we are done. That is the cyclic subgroup, and this power, where we hit the identity, that's the order of the element. We go till we hit the identity the first time. And we looked at a proof that if we get any kind of repeats, somewhere before we notice a repeat, the identity should occur. So if you're working through this and you get a repeat and you haven't seen the identity yet, something's wrong. Because you should not see any repeats until you actually hit the identity. And after the identity, you should only see repeats. That's the idea of the cyclic subgroup once you hit the identity. If we do alpha again, we're back here, again, we're back here, again, we're back here. And in fact, once we decide it's 6, we're kind of on a 6-hour clock. You know, alpha to the 23rd will be the same as alpha to the 5th. Alpha to the 45th would be alpha to the 3rd. 45, we go around 7 times with a remainder of 3. So there is kind of a connection with cyclic groups with what we've been talking, you know, the clock arithmetic. Okay. Other questions?
How would you like us to, like on number 3, how would you like us to show that it's going to log it onto?
Okay.
You said like, how do you know, is what you wrote on here, like, how do I know it is?
Yeah. I mean, we could refer to a graph. If a graph is applicable, we could refer to a graph. Or, what I also saw in number 3, 3, our mapping was a squared for 1 to 1. We could assume theta of A equals theta of B. So A squared equals B squared. And hope to conclude that A has to equal B. Well, with squareds, what we'd like to do is take the square root to get rid of the squares. If we were doing all reals, that could be a problem, because we don't know whether A is positive or negative. However, here, that's not a problem, because A is positive. Square root of A squared is A, the square root of B squared is B. So if we somehow ended up at the same spot, we really had to have started from the same spot. And for onto, it's do we get all the possible outputs? So say we want to get C, can we figure out how we get C? So can you figure out what input would give us C? And I guess we could take through this theta of A is A squared. Well, if A squared is going to be C, A's got to be the square root of C. So if I plug in the square root of a number, that's the number I'll get out. So you want a particular output, I can produce it. You want pi, take the square root of pi. Glad I thought of pi. Pi day, March 14th. Yeah, I didn't bring any pi, but
How would you get a square root though, if you wanted a square root?
what do you, how would,
Since we're dealing with the reals, if you put in a square root, you're gonna get just the number because it's squared.
well, what's the square root of a square root? So if you wanted to say the square root of 2, can we do the square root of the square root of 2? Is that still a real number? So,
That last line, wouldn't it be the theta square root of C equals A?
I mean, C is what we want to get out, so I'm replacing A by the square root of C. The idea of onto is you're given an output, and you're trying to figure out, can I figure out where it comes from? What is the input that would produce that output? So,
Another question with that was on the problem. It just said that asked as if the theta is an isomorphism. Does that just imply we need to show it is one-to-one onto?
Yeah, for being an isomorphism, it needs to be one-to-one onto, and it needs to preserve the operation. And in fact, I should probably kind of run through that as well, because, so in terms of preserve the operation, if we combine the elements first, do we get the same thing as if we map first and then combine? So that's the question we need to address when we're talking, does it preserve the operation? So in this, the mapping is square the input. So if we map or combine first and then map, we get the AB squared. If we map first, we get A squared and B squared. Are those the same? Well, if we were talking in general, there'd be a problem here because it actually involves commuting. Are we talking in general? Here we're looking with positive reals under multiplication. That multiplication is commutative. So, I mean, this is one of our properties of exponents we learn in algebra. If you've got a product to a power, each factor could be raised to the power. It's the same expression. That works fine as long as we're in a commutative group, which we happen to be here. We don't have that many non-commutative groups to talk about. Permutations is the biggest non-commutative family we have to talk about. Most of our work is going to be commutative. So, in this case, they are equal, the operation is preserved.
When would it not be equal?
Okay, well, so suppose we were going, say, the reals under addition to the reals under addition. Same mapping. So if we combine two elements, do we get the same thing as if we map first and then combine? So if we add them first and then map, we get A plus B squared. If we map first, we get A squared and B squared. And then combine them. Are they the same? Now, here the answer is no, they're not the same. Although a beginning algebra student would look at that and say, well, if they're the same there, why aren't they the same there? I mean, if you've ever tutored somebody in algebra when they first see this is kind of what we'd like to have happen. And we have to say, well, no, when you multiply with the addition in there, think of the FOIL technique, or, I don't know if any of you have seen this model. Say A plus B, as a rectangle or I guess a square. And if we think of the area, what's the area of this whole square? A squared. This one? AB, AB, and B squared. So what's the total area? Yeah, the A squared plus 2AB plus B squared. Same type thing we get from FOIL, but it's a little bit more visual demonstration of how we multiply those two binomials. And in a sense, that's also the idea that we use when we multiply two-digit numbers. We don't use that as our algorithm for multiplying two-digit numbers, but say 26 times 32, 20 and 6, 30 and 2, 600, 180, 140 and 12. Total area is the sum of all that. Our typical algorithm of, say, 32 times 26 is 196, and notice, how about 192? Notice we do have 192 there. And then, 64? or 640, we do have a 640. It just kind of splits it up and breaks it up a little differently to get our final result for the product.
So a little side note, does that visual representation work for cubing as well?
For cubing,
Or is it different?
well, it probably works for cubing, but I'm not sure I can draw a cube and think of the eight spots for the cube.
What if you just did
So-
A,
so-
B, and C?
Huh?
I'm sorry, what if you just did like A, B, and C? Like would that all end up?
Well, A, B, and C would be more like then, say, A plus B plus C times A plus B plus C. I think that would work fine,
It's just two.
but it's still just the product of two things.
Yeah.
I think if it's the product, if it's cubing, we would need to kind of think of an A plus B back here, and can we figure out what the 8 cubes look like? And my spatial geometry is not that good to do that. I mean, so I guess, I don't know if I really want to attempt this. I mean, we do have an A cubed here, right? From sort of this front cube, A by A by A. We've got A squared B, A by B. In fact, I've got A times this front face, so an A squared B and an A B squared, and then I've got B times the front face. So A squared, or no, A squared B. Gets hard even to write it in here. AB squared. So I think the answer is yes, it would work, but I don't think it's a helpful visual in that case, trying to figure out where do I put those 8 cubes. And then we think, what about A plus B to the 4th? Well, I can't visualize that in 3 dimensions. I sure don't want to try to go to a 4-dimensional cube to figure out what's happening. I have videos I could pull up to show you about drawing higher dimensions, but I don't think I want to blow your mind that much before your test on Friday, especially on something that doesn't really relate to the test. Well,
Yeah. I got you.
so.
The test still consists, are all the topics on this homework?
Yeah, I don't think there's anything on the test that's not already on this homework.
Okay.
I mean, there would be definitely a different function to tell if it's an isomorphism or not, and could be a different group to work with, different mappings, different permutations, but it's going to be the same, very much the same type of questions. Did you have a question? Or?
I did earlier.
I was thinking you were about to ask when I got another one, so.
Oh, for the E, or 2E. So the fifth subgroup in that case would be all of the alpha prime, alpha cubed.
Well, alpha squared, alpha cubed, alpha to the 4th. Yeah, we would keep multiplying by alpha till we got the identity.
Okay, so the order would just be where the identity shows up. Subgroup would be everything.
Yeah, including the identity itself. Once we hit the identity, we're done. And that's what happens really with on 4 as well. We know if 7's the generator, we start with 7, combine it, do it until we hit 0. Once we hit 0, we're done, because after that, we'll be back to 7. So the question on number 4 would be, if we start with 7, do we get them all before we hit 0? It's really the question for any cyclic subgroup. You'd ask, would we have to tell if it's cyclic? Try something as a generator. You're either going to, you will hit 0, or the identity. The question is, do you hit the identity before you get everything, or do you actually get everything by the time you hit the identity? If you get everything by the time you hit the identity, it is cyclic, and we can make a determination about everything based on that. If we hit the identity before, we need to try something else. And we either exhaust all the possibilities, or we discover a generator. Okay. Other questions? Yes.
When doing, like finding the generators and that whole thing, when do we, like, go until we find 1, and when do we go until we find 0? Sometimes it changes.
If our operation is addition, the identity for addition is 0.
Okay.
If our operation is multiplication, our identity is 1. If our operation is the composition of function or permutations, our identity is the identity mapping. If it were some other operation in some other group, it would be whatever the identity is there. And I will not be asking you, well, actually, there is one I potentially could ask. We've looked some at groups of ordered pairs. So, Z3 cross Z4. And we'll do addition in both. What's the identity in this case? We're working with all the elements are ordered pairs. So what's our identity here? 0, 0. So on this one, we would go until we hit 0, 0. So if we started with, say, I don't know, 1, 1, we'll get 1, 1, 2, 2. What do we get next? 0, 3. What, 1, 0. 2, 1, 0, 2. 1, 3, 2, 0. But by this point, we're over halfway. We're going to get everything. We can kind of 0, 1, 1, 2, 2, 3, 0, 0. That's where we stop. And I think we've got all 12 elements. So this is a generator. What are the other generators?
What is the fifth position?
The fifth position. So yeah, so if you think in terms of positions, the fifth position, because that's relatively prime with 12. 1, 2, 3, 4, 5. That's another generator.
And the seventh.
The seventh position. And the 11th position. Those are our other generators. What's this one going to generate? How big is it going to be? How big is the subgroup it's going to generate? We're in the, what, 10th position?
Maybe 2.
Well, the greatest common divisor of the position and 12 is 2.
Also 6.
So the size is 6. The divisor times the size equals 12. So this is going to generate a subgroup with 6 elements. We can double check that. And in fact, as long as it's fairly small, we could brute force it and just try them all. We don't have to, but we could. But there is a pattern once we have a generator that would tell us what everything else does based on what's the greatest common divisor of the position and 12. is the greatest common divisor of the position and the size, or the size of the big group, times the size of the subgroup, equals the size of the big group. So greatest common divisor here was 2. The size of the subgroup then would be 6. What would the size here be in the 8th position? I think I heard a 3. 8th position with 12, greatest common divisor is 4. Now, that leaves a subgroup with 3 elements. And again, if we'd like to, we could double check. Yes, it really has 3 elements. Let's see, 2, 0, 1, 0, 0, 0. 2 plus 2 in Z3 was 1. And notice the other generator here would be 1, 0, which happens to be in the 4th position. So there are a lot of connections going on here if we recognize them. So this is another group that we've worked with some that's a bit more abstract, but at least we are dealing with numbers. And for that matter, we're adding them. A little bit different than we usually add, and in fact, different in the first element than the second element, but at least it's numbers and an operation we're familiar with. Whether we remember and keep all that straight when the time comes, then that's another question, but it is addition modulo, on a 3-hour clock and on a 4-hour clock, as we work with this. So we can work with ordered pairs. Would be another possibility for groups. So I mean, in terms of the groups that could show up, I mean, permutations are going to show up a lot. That was about half this homework set. That will definitely show up a lot. But other groups that could show up, Zn, and we work with addition and multiplication. With multiplication, we threw out the 0. Also with multiplication, sometimes we threw out other elements. We can work with ordered pairs. I think that's about all we'd work with.
I'm not able to read that equation on the very top in red. I can't read it very well.
Okay, the greatest common divisor of the position and the size times the size of the subgroup equals the size of the group.
Position and size.
The greatest common divisor of the position and the size
Okay.
of the group times the size of the group, size of the subgroup. So we've got to watch our sizes, because there's the size of the big group and the size of the subgroup we're generating. Okay. Other questions? Let's see, in honor of Pi Day, I'm not going to sing the find the digits of pi that Lesser wrote, among his lesser greater hits. Actually, I may not be singing anything because I failed to log in yet this morning. Surely I can do that quickly enough. Maybe. probably one of the first math songs I ever stumbled upon. I can still remember singing it one time, and I had a student that actually heard it twice. It was Pi Day, so I went to another class to do it, and got 1 point, and she starts laughing hysterically. You know, before I got to the part that she's found so funny, but she knew it was coming, and she's just laughing hysterically, and everyone in the class is like, what's wrong? But to find a circle's area will often make you queasy. It's not just simply linked by width or anything that easy. But then one day you'll find a number that will help your brain. It might be transcendental, but it's sure to save you pain. Oh, 3.141592653589. If you were to say it all, then we'd be here a long time. Multiplied by 2r, then you will have a curved line. 3.141592653589. Aristotle, 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 pi. Aristotle, 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 pi. If you were to write pi to several 100,000 digits, any who saw patterns there, I'd have to say were idiots. The proof that pi's irrational is just too long for now. But if you'll ask your math teacher, I'm sure he'll show you how. Oh, 3.141592653589. If you were to say it all, then we'd be here a long time. Multiply by 2r, then you will have a curved line. 3.141592653589. Aristotle, 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 pi. Aristotle, 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 pi. So if you have a sphere whose volume you must quickly know, it's simply 1 1/3 pi by r cubed, don't you know? But better use it carefully or pi can lose its gloss. For instance, one night I used it on some trig, and now my sign's a cos. Oh, 3.141592653589. If you were to say it all, then you'd be here a long time. Multiply by 2r, then you will have a curved line. 3.141592653589. The end. Friday, I will plan to be here 7:30, if anybody wants to start early. I don't think the test will take longer than an hour, but there's not a class in here at 9. If you can stay, that's fine. And I will see you for the test.